All right, on to lecture 26, part B. So we're kind of done talking about intermolecular forces. There's one more little topic, though, that kind of goes along with it, and that is, excuse me, that is looking at how much energy it takes to take like a solid and turn it into a liquid, and a liquid turn it into a gas. So that's what we're going to kind of work out on in this lecture, lecture 26, part B. I should tell you there is a little math involved, so if you have a calculator handy, that might be helpful. So before we get to any math, though, let's just go over a few terms that I want you to be familiar with. So there's three states of matter. Some things in the world are solids, some are liquids, and some are gases. Now, you can take a solid and you can turn it into a liquid. You can take a liquid, you can turn it into a gas. You can also go in the other direction, right? You can take a gas, turn it back into a liquid. You can take a liquid, turn it back into a solid. So all of these, when we change from like a solid to a liquid or a liquid to a gas, there's words that go along with that. So if you take a solid and you turn it into a liquid, most of these words are not like crazy fancy chemistry words. They're like everyday words. If you take a solid like ice and you turn it into a liquid like liquid water, what's that called? Oh, you're melting. You're melting the ice. You're melting the ice. All right. So that's just taking a solid like ice, turning it into liquid water. Now, what if you take like liquid water and you turn it into a gas? What's that called? Well, that one, usually you might call it boiling. That's true. This one there is sort of a fancy chemistry word for. So you could boil water, that turns into a gas. Usually in chemistry, we call it vaporization, where you vaporize water. Vaporization. All right. Now, you can also go the other direction. You could take a liquid, turn it back into a solid. You can take liquid water, turn it into an ice cube. What's that called? You take liquid water, you turn it into an ice cube. Liquid to solid? Oh, that's freezing. Now, what about if you take a gas and you turn it into a liquid? That one, maybe it doesn't happen too much. You don't probably do that too much in your everyday life, but it does happen outside all the time. There's like moisture in the air, gas in the air, liquid water, well, I say water vapor in the air. And that water vapor, if it hits something cold like your car, it'll turn into liquid water, the gas, the water vapor in the air. So when that happens, you might go outside, you might go, oh man, there's a bunch of condensation on my car. So this is called condensation. So condensation is when you, or I guess we'll call it, kind of changing tenses here, condensation is when you go in the other direction. All right, so what does this have to do with, we just spent all this time talking about intermolecular forces. Why is this related at all? Well, the reason is as we go across to the right, as we go from a solid to a liquid, ice to water, or liquid to a gas, boiling water, when you're doing that, you have to add energy. And what you're doing with that energy, you're actually breaking the intermolecular forces between molecules. So you're splitting apart the molecules to get it to turn into a liquid or to get it to turn into a gas. Now, if we go the other way, by the way, if we go the other way, if you take a gas and you turn it into a liquid or a liquid into a solid, to do that, you actually have to cool things down, right? And another way of saying that is you're actually removing energy. And when you remove energy, what happens there is you actually, these intermolecular forces get a chance to reform. So you form intermolecular forces as you go the other direction. All right. Now, really, again, what we're going to do in this video, we're going to talk about calculating how much energy does it take to take a solid and make it into a liquid? Or how much energy does it take to take a liquid and turn it into a gas? So the way to do that, there's a number that goes along with taking one kind of substance and turning it into a liquid, or another kind of substance, like a solid to a liquid. And the energy it takes, they have a name. So the energy to take a solid and turn it into a liquid, that energy it takes is called the, well, maybe I should switch colors here, the heat of fusion. That's the energy it takes to have a solid turn into a liquid. There's a symbol for it, by the way. It's delta H FUS for fusion. Now, if you want to take a liquid and you want to turn it into a gas, and you want to know how much energy does that take? How much energy does it take to boil something? Well, there's a number that goes along with that, and that one is called the heat of vaporization. And again, there's a symbol for that, delta H vape. All right, so we're going to look at a chart that kind of helps us know how much energy it takes to do these, and then we'll do a few calculations to actually calculate the amount of energy. All right, so let's go ahead and let's get to those charts. Let me show them to you. They'll help us with this topic. Let me flip over. Okay, so this is a table out of your textbook, the TRO book, and this is the table of heat of fusion. So what is this table going to help us with? This is going to help us when we want to calculate how much energy does it take to take a solid and turn it into a liquid. A solid and turn it into a liquid. I should tell you, it also is the energy that is involved going the other way. So when you take a solid and turn it into a liquid, you have to add energy, and this is going to tell us the amount of energy. And then if you go in the other direction, it's really going to also tell us the amount of energy you need to lose if we're going to take a liquid and turn it into a solid. So it works for going either direction. It's the energy involved that you got to add if you're making a liquid, or you got to take away if you're making a solid. All right, so I should tell you they list several things here: water, alcohol, acetone, and so on. They do tell you the melting points. That's not going to really be anything we're going to worry about right now. Really, the column you need to focus in on is the last one, heat of fusion. That is the energy it takes to melt something. So you notice that for water, it says, for example, 6.02, and then this is the units up here, kilojoules per mole. So when we do some math in a few minutes, you might be better off thinking about those numbers as actually kind of a conversion factor. So when you see kilojoules per mole, another way of thinking about that for water is that it says 6.02. That would always be the number of kilojoules it takes to melt equals 1 mole of water. So you could write it that way instead. Instead of a slash, you could think, oh, that's equals to 1 mole. Or for alcohol, the amount of energy it takes to melt alcohol is 5.37 kilojoules will melt 1 mole of alcohol. And for acetone, it's 5.69 kilojoules will melt 1 mole of acetone. All right, so I'm going to show you another table in a minute. So you might need to, when you try some of these problems, you might need to make sure you're using the right table. Heat of fusion, that has to do with taking a solid, turning it into a liquid. All right, another table has to do with vaporizing. That is taking a liquid and turning it into a gas, or maybe going the other way. If you go this way, this is the amount of energy you got to add. If you go the other way, this is the amount of energy you got to lose. So again, you see several things listed here. You see water, alcohol, acetone. It's actually the same things, isn't it? This chart, heat of vaporization, has to do with liquid to a gas. Again, there's several columns here. The ones that we're going to focus in on is we're not going to ever really use the boiling point. They just tell you when these things boil. So this column isn't going to be super helpful. And we're actually probably not going to use this column, at least not in this video. The one that we're going to use is the one where it says heat of vaporization at boiling point. So that would mean, like, if you have a water and it's 100 degrees, how much energy does you got to add, even when you get it to 100, how much energy do you add to get it from a water at 100, liquid water 100, to water gas, water vapor at 100? How much energy does it take to get it to turn into a gas? So again, you'll notice there's the column here, and the units are kilojoules per mole again. So for water, it takes 40.7 kilojoules to boil 1 mole of water. Acetone takes 29.1 kilojoules to boil 1 mole of acetone. All right, so with that, let's go ahead and we're going to do a few examples of calculating the energy it takes to take something and turn it into a different state, a solid to a liquid or a liquid to a gas or whatever. All right, so let's flip over to our examples of doing that. Okay, first question here. How much energy is required to melt 4.5 moles of ice? How much energy is required to melt 4.5 moles of ice? Now, they also tell us the molar heat of fusion of water is 6.02 kilojoules per mole. All right, so first off, is that the number we're going to need? Fusion, yeah, heat of fusion, yeah, that's the energy that involved going from a solid to a liquid, yeah, and yeah, that's what melting is. So yeah, that's the right number. We wouldn't need the heat of vaporization. We're melting something, so we use the heat of fusion. All right, now, basically, again, this is going to be a calculation, and kind of like we've been doing pretty much all semester, with a few exceptions, we're going to think of it as converting. How much energy is required to melt 4.5 moles of ice? So you're starting off with 4.5 moles, and I guess ice, if I want to write ice, that's really water, right? H2O. And I'm trying to solve for how much energy. Now, energy is measured in, at least in this chapter, we tend to use kilojoules as our unit of energy. So we're really trying to solve for kilojoules. All right. 4.5 moles of water, how many kilojoules does it take to melt it? Now, the other thing I want to point out to you is we need a conversion factor. The conversion factors are like in those tables. Now, again, to make it a little easier, I'm not going to go back to the table and show you. I just gave you the number off of this table. This is the same one you see, I think, in that first table I showed you. 6.02 kilojoules is the energy it takes to melt. Another way of saying that is equals 1 mole. Melts 1 mole of water. Always equals 1 mole. All right, so let's go ahead and work it out. So again, it's converting. We haven't done one like this, but man, we've been doing converting. If you start off with moles of water and you're trying to get rid of moles of water, oh, that means you put it on the bottom. And that means you're going to put the 6.02 on top. So you multiply by 6.02. That should give us our answer. Oh yeah, does that work? I think so. Moles will cancel and we get kilojoules. I worked this out a little while ago. When I worked it out, I got 27.1. That's what I got, 27.1. All right. So this one, we went from basically, let's see, the moles, and we solved for kilograms, didn't we? All right. Let's do another example. Let's do another one. Let's do another one. All right, so this one is how much energy is required to boil 45.5 grams of water? And then they tell me the molar heat of vaporization of water is 40.7 kilojoules per mole. So yeah, I guess they're telling me that, right? So you won't have to go back and look in the table. So let's just double check that's the right number though. Vaporization. Oh yeah, heat of vaporization. That's when you're going from a liquid to a gas. Oh yeah, that's vaporizing. So yeah, that's the right table. Wouldn't use the heat of fusion. That's for melting. We're boiling. So yeah, that's the heat of vaporization is the one we want. Now in this one, let's see here. We're gonna convert again, basically, right? And I'm solving for energy. How much energy? So we want to get to kilojoules. Now I should mention this one's a little tougher than the last one, right? Do you notice why it might be a little tougher? Well, I've given you this number. This number will get you from kilojoules to moles. 40.7 kilojoules is a mole. But you don't have moles now. You have grams. 45.5 grams is the number you're starting with. So you, in this one, you're going to have to do a little extra work. You have grams of water, 45.5 grams of water. So you're going to need to go from grams to moles. And then we can go from moles to kilojoules. So how can you do that? Well, grams to moles, oh, we've done that before. That's your periodic table, right? And then moles to kilojoules, you would use your table. You would use, well, this number. Usually you get it from the table, the 40.7 number. All right, so let's go ahead and let's work it out. So yeah, 45.5 grams of water. Let's convert it to moles. And then once we get to moles, then we can use the heat of vaporization to get our answer, our kilojoules it takes. All right, so grams to moles. Oh, we got to add up the weight off the periodic table. Let's go ahead and do it. Let's see you would do water, H2O. That's 2 hydrogens and 1 oxygen. I'm just using the numbers under the symbols. Yeah, we haven't done this in a while, have we? 16 for oxygen. Oh, if you put it all together, you get 18.016. Oh, 18.016. I'm going to write it down here because I ran out of room. 18.016. What? Grams equals a mole. All right. So we can use that to go from grams to moles, can't we? Oh, let's check. Do you remember? Are you going to multiply or divide by 18? Divide. You would divide by 18. Now you got moles. So now we can use, well, kind of our newer number, the one we haven't really seen much, that number, the heat of vaporization, to go to kilojoules. So what are you going to do next with that 40.7? Do you need to multiply or divide by it? Multiply. So you would put the 1 mole on the bottom, and you put the 40.7 on top. It should look like that. Oh, kilojoules, shouldn't it? Now, does that look right? It does to me. Grams, by. Moles, by. You're left with kilojoules. How much energy? Yeah, energy, we're looking for kilojoules. Now, I worked this out, but I just realized I used a slightly different number. Let me double check that I have the right answer. 45.5 times 40.7 divided by 18.016. Yeah, that's what I got, basically. 103. You should get 103. Rounded and everything. All right, hopefully that makes sense. Do you know what? Let's just practice one. Let's just practice one more. Make sure you got this figured out. Let's put up one and maybe you can work on it this time, huh? Okay, our final example on this topic. How much energy is required to melt 14 grams of rubbing alcohol? And then they tell me the, I guess the formula of rubbing alcohol, right? How much energy is required to melt 14 grams of alcohol? All right, now let's see what they've also given me. The molar heat of vaporization of rubbing alcohol is 39.9. The molar heat of fusion of rubbing alcohol is 5.37 kilojoules per mole. All right, so I'm supposed to figure out how much energy. So another way of saying that is kilojoules. How many kilojoules is it going to require to melt? All right, now melt. Now remember, there's 2 different values. Heat of vaporization and heat of fusion. If you're trying to melt something, which one are you using? If you're trying to melt something, should you use the heat of vaporization or the heat of fusion? One of those two. Which one are you going to end up using? It should be the heat of fusion. Heat of fusion has to do with taking a solid, turn it into a liquid. Hey, yeah, that's called melting. All right. So yeah, this is the number that's going to help us. This one we're not needing. We're not boiling anything. We're melting it. All right. So, okay, that's one good thing. So this tells me for alcohol, it takes 5.37 kilojoules to melt alcohol, a mole of alcohol. Now, just like we did a minute ago, if you start off with 14 grams of alcohol, before we're going to be ready to use that number, the number that has moles in it, we're going to have to convert grams to moles first. So to do that, we're going to have to add up the weights off the periodic table for alcohol. Now let's go ahead and do it. 3 carbons, 8 hydrogens, and an oxygen. 12.01, 1.008, 16. Oh yeah, are those the right numbers? I hope so. Yeah, those look right. Let's put it all together. 36 and 8.064 and 16. The grand total is, oh, I'm going to have to work it out. I don't have this in front of me. 36.03 plus 8.064 plus 16 adds up to, yeah, a little over 60. Oh, and what the heck is that? 60.094. That's how many grams equals a mole. Always, always, always for the rest of your life. That's how many grams equals a mole. So at this point, we've got our 2 conversion factors. We've got one that gets me from grams, which is what I have, 14 grams of alcohol. This is going to get me from grams to moles. And then we got the one from the tables that tells me about, well, going from moles to energy, moles to kilojoules. I'm going to write it down here again. All right, so these are the two you're going to use. All right, do you know what? I'm going to let you figure it out from here. Let's see if this is making sense. I hope it is. I'm going to rewrite this just a little bit. All right, let me just get it set up for you just a little better, so that might help you. I want you to figure out this answer. All right, work it out. See what you get. We'll do a little pop-up question here. Okay, hopefully you got it. All right, so hopefully you got it. Let's see. So grams to moles. Oh, use your 60. I hope you divided by it. If you divided by it, that was the right idea. By grams. Now you got moles. Moles to kilojoules. We're going to use the 5.37. 1 mole goes on the bottom. The 5.37 goes on top. Gosh, I don't even know what the right answer is. Let me work it out. 14 times 5.37 divided by 60.094 equals, it's going to be about 1.25 kilojoules. That's what I got. I hope you got that. 1.25. All right, so that's it for this video. You can tell the lectures this week, they're a little shorter, huh? This chapter, there's not quite as much in it. It's like a little too much for one lecture and not quite enough for 2 lectures. So there is no part C. So you are done with lecture 26. As usual, if you're having any issues or questions or concerns, you can email me. I'll try to help you out. Otherwise, I'll see you in our Zoom session soon, and we'll get a little more practice. And we might do one new topic in Zoom that I didn't talk about. So I'm still thinking about it. We'll see. I might bring up one more topic, but in Zoom instead. All right, for the videos, we're done. Have a great day. I'll see you next time.